Murphy, and from Princeton University. As you probably know, she was one of the MCA Prize winners, and she will lecture on flexibility in contact geometry.
Great, yeah, thank you very much. Thank you for the introduction, and of course, the invitation to talk and all of this, and it's quite an honor with all of this. Of course, I suppose it's like a compulsory thing to say at the beginning of these that like, wish I could be in Buenos Aires, but well, of course, we're all making sacrifices. So yeah, anyways, so I wanted to talk about something that's kind of I guess, a little bit of a survey of the last 10 years of work or so. I guess it's maybe a bit of an old story for people who are experts in the field, but I'll maybe kind of introduce it with kind of a bit of a new perspective than what I have before. So yes, so I want to talk about just Lagrangian manifolds in Cn. And so a Lagrangian submanifold is just any submanifold, so that if you take its orthocomplement, that's the same thing as just like multiplying by I. And so the kind of clear examples is just like Rn inside of Cn, or also you can get a torus just by taking a product of any collection of curves in Cn, in C, and then just taking the product. So this is something that looks, essentially like locally like Rn inside of Cn. And notice this is kind of a metric condition. It's not just a condition on the complex structure, because I'm asking for orthogonality, not simply, that it's linearly independent. So it's a closed condition. And so a major question I want to talk about today is just what diffeomorphism types, well, say of three manifolds or of other kind of related questions, admit Lagrangian embeddings. So for three manifolds, we're talking about into C3. So a major kind of starting point for really anything that's kind of modern symplectic geometry is a theorem of Gromov, which says that any closed Lagrangian embedding is necessarily has non-trivial first homology. And in fact, this can kind of be made more precise, and that there's a kind of like action class, which is non-zero. But that action class anyway is a first de Rham cohomology class. So that rules out, for instance, S3. And now, since Gromov, we've kind of like built up more and more sophisticated tools to kind of study this sort of question. One of my favorite is a result that's due to Fukaya, and really, I think a lot, some important details also due to K. Erie. And the theorem is that if you have any prime three manifold, so a manifold which isn't a connect sum of other manifolds, and that is embedded as a Lagrangian into C3, then it has to be a product of S1 with a surface. So that's kind of extremely restricted, right? Like, I mean, of course, prime three manifolds, or even hyperbolic space forms are kind of quite large. Of a, I mean, this is a very small subset among prime three manifolds. Now, what I want to contrast this with is the kind of flexibility side, which is a theorem due to my collaborators and myself, which is that if you have any manifold and you just connect sum a single copy of S2 cross S1, then it does admit a Lagrangian embedding. So on the other hand, while in some sense Lagrangian embeddings seem extremely restricted by this geometric condition of being Lagrangian, on another hand, like if you have just like this single copy of S2 cross S1, everything just kind of, you can make anything you want. Here, M can be kind of an arbitrary, rational homology 3-sphere that's kind of like an extremely large class just by itself. Okay, so now this particular result isn't the main focus, but really the main focus I want to talk about is this sort of dichotomy, this sort of a situation where you have that, like, the geometry makes things extremely constrained, but then if you just loosen one sort of funny hypothesis, then suddenly kind of anything becomes possible. And that's really the kind of theme of this lecture. So yes, so another example I want to talk about is, so Gromov already told us that we can't have anything with kind of trivial first cohomology, but now I'm going to assume that that I do have something, which is kind of, I could even assume it's simply connected. That's fine, but whatever. H1 is 0. So there's no embeddings, but there may be an immersion. And so if there's an immersion, a Lagrangian immersion of L, then of course I can make it kind of transverse to itself at every point. And then, so there's only like some finite number of double points. And I could use that as some sort of measure of complexity, right? Because I know there can't be none of them, I guess. So the first thing I can do is I can just study, okay, what are all the possible immersions of a manifold that have only a single double point, which is transverse. So I can't have no double points, but I'm assuming that I just have one. And now just to kind of, I don't know, add a bit of flavor to things, I'm going to assume that the dimension is even. So using some just very simple kind of algebraic topology argument, it follows that the Euler characteristic has to be plus or minus 2. And that depends on whether that double point is an even, is a positive double point or a negative double point in terms of the kind of orientation self-intersection. So again, I want to contrast two results. So there's a result due to Ekholm and Smith, which says that if this is a positive double point, then necessarily L is a homotopy sphere. And in fact, much more than this is true. So if we're talking about S4s, of course, 4-dimensional topology is kind of like a crazy thing. But if we're talking about high-dimensional topology, then in fact, L is not only a homotopy sphere, but it's diffeomorphic to the standard sphere. It's not even like an exotic sphere. So that's kind of an extremely constrained situation, just this condition of being Lagrangian. Now, what I would like to contrast this with is that if you have any smooth manifold which has Euler characteristic -2, so now if we switch our condition to where we have a negative double point, then, well, there's one certainly necessary condition, which is that the complexified tangent bundle has to be trivial because, we have an immersion into Cn, and, the fact that it's Lagrangian tells me that the normal bundle is isomorphic to the tangent bundle, right? But so this is clearly a necessary condition, but that's all we need. We can be any manifold. Just the tangent bundle needs to be trivial. And then there's this Lagrangian immersion. So there's something which seems quite strange because, we're just talking about a double point, whether it's kind of a positive or negative double point, which is just like an orientation condition, but that completely changes the sort of available topologies which are able to be embedded in this kind of real half-dimensional way, I guess. Great. So yeah, that's again, just kind of a couple of things. Maybe to build some intrigue, I guess. That I guess, again, what I'm wanting to highlight here is that the situations are just so distinctly kind of stark from each other. Maybe this is a great place to pause for questions, if anyone. All right, wonderful. All right, so yeah, something I want to especially point out is that on the constructive side here, so the things where we're saying that embeddings or immersions do exist, we don't need like many double points or like many of these S2 cross S1 summands. We only need like a single copy, no matter how complicated the topology is of the rest of it. And that's really kind of something else I want to highlight in this talk. Which is kind of a strange thing. So something where, where you can kind of do things if you allow like sufficiently many kind of weird singularities that help you do things. Well, that's actually pretty common in a lot of different geometric phenomena. But something where just a single copy of things suffices to build arbitrarily kind of many exotica, I guess, is more unusual. This pattern, though, is in fact common, particularly to symplectic geometry and as well as some related geometries. So yeah, and in particular, this sort of dichotomy where we have that, given some basic hypothesis, if the manifold is prime, if we have only positive self-intersections, there are many such things. The geometry becomes extremely constrained by a sort of number of equations, particularly using pseudo-holomorphic curves and floor theory. However, this is kind of extremely delicate in that it can be sort of destroyed by a kind of just a single compact shape, for instance, this kind of double point or the S2 cross S1 summand, which will sort of make all of the interesting geometry kind of disappear because it can kind of account for anything within this one shape. Yeah, so I think that's an unusual phenomena within geometry, and so that's a big part of what I want to explain. So because this is a symplectic sort of phenomena, I need to talk a little bit about what symplectic geometry is, I guess. And this is famously, like, I guess, a little bit opaque. So the very quick and sort of, I guess, dirty definition of symplectic structure is it's a two form, which is non-degenerate and closed. That can be very hard to understand, I think, why that's a good definition if you're not familiar with these things. I think the best sort of intuition kind of starting point is to think about Kähler manifolds. But thinking about symplectomorphism is kind of like a weaker notion. So if you're not so familiar with Kähler geometry, so one way to think of it is that what the symplectic form is doing is it's kind of measuring to what extent one vector, so, first of all, it takes pairs of vectors and it gives a number, and it's kind of measuring to what extent a pair of vectors that one is j times the other, right? It's kind of measuring parallelism after multiplying by j, right? Like it's kind of the imaginary part of a Hermitian form. So it's kind of, very similar to complex geometry. However, because of the, because it's skew, that makes it a two form, which makes it a bit more topological. So a good way to think of this is kind of like floppy kind of complex or Kähler manifolds in particular. In particular, this condition of being Lagrangian, so I introduced this as kind of, something which is kind of totally real, looks a lot like Rn inside of Cn in terms of its orthocomplement being just its, I guess, multiplication by j, but in fact, that's a symplectic property, which makes sense because it's kind of interpolating j and the inner product, right? Which is kind of what that is doing. Okay, so now I want to talk about a different example that's a bit more symplectic. So I'm going to be talking about a class of hypersurfaces in C4. So given any positive integer b, I'm going to define the manifold xb to be the complex hypersurface cut out by this polynomial equation. It's smoothly cut out. It is symplectic because it inherits the symplectic form from C4, which is just, the kind of standard Fubini study form. One reason to kind of like this class is that for any B, the diffeomorphism type doesn't change. It's just S3 times R3. All right, so this is just kind of a class of examples, but one result is that if we're just studying the symplectomorphism type, so of course the algebraic isomorphism type is quite different for any of these, but the symplectomorphism type actually depends on B. So XB is not generally symplectomorphic to X1. So this one way I think it's nice to kind of highlight this theorem is, so that really is how you distinguish X1 from the higher XBs, is that X1 is just a smooth quadric, right? It's just a, so we can write it instead in different quadric coordinates. And I like these coordinates because we see that there's a Lagrangian S3 in here explicitly, right? And a Lagrangian S3 is kind of interesting because at least it tells us that that we're not the same thing as C3, first of all, by Gromov's theorem, and also we can't embed into C3 even, right? So a Lagrangian S3 is kind of a fundamental building block, which this X1 contains. However, the other XBs contain no such, which is really what Majdansky and Seidel's theorem is proving. However, that distinction completely disappears with the higher Bs. So if you look at X2, X3, X4, X5, those are all the same manifolds symplectically. They're all symplectomorphic to each other. So now again, this isn't precisely about Lagrangians. This is about symplectomorphism types of whatever these complex threefolds. But again, this has the same sort of flavor, right? Of you have this kind of geometric distinction. However, you have that kind of, as soon as you have a little bit of something, then kind of everything becomes just this sort of the same, and you kind of lose the interesting geometry. Yeah, it's not so clear exactly why or if these results are directly related, but it turns out they are, which is something I hope to highlight. Okay, great. So another thing about these, so we have this, this kind of one parametric family of manifolds. So now something else I want to talk about is the embeddings of these things. So the first thing I'm going to do is I'm just going to intersect them with a ball of radius 100. That's just to get a compact bounded space, because I want to talk about embedding it into other spaces. So that's, just, that's just in order to ignore things like going to infinity questions or whatever. Now, as I mentioned before, there's no symplectic embedding of this X1 into C3 because, well, X1 has a Lagrangian S3. C3 doesn't by Gromov's theorem, so one doesn't embed into the other. However, X2, and therefore all the higher XBs, do admit symplectic embeddings into C3, which is a bit surprising. So again, this is kind of a phenomena of the exceptional one has this kind of interesting geometric obstruction, whereas these the kind of random ones all kind of lose their geometry and there's no obstructions to kind of doing anything. And in fact, we see this in kind of a much more general sense. So this is, again, just sort of an example of a theorem we can prove. But if you have any symplectic six manifold, just like anything at all, and you have a smooth embedding of, just S3 times a 3 ball into the manifold. So in other words, I just want to start with any symplectic manifold, and then I have just some smooth embedding of this diffeomorphism type. Then there is a symplectic embedding of this X2 into M. I need to rescale just for volume obstructions, for instance. I need to assume that the total volume of M is at least the total volume of this X2 bar. But despite that, so up to scaling, we can in fact embed this X2 into anything, into any smooth class. So I guess what I'm wanting to say is that this is not only kind of a particular symplectic embedding into C3, but in fact, these things are kind of quite general. And of course, this X2 bar is only a single kind of example. All right, so yeah, so now again, well, I'm gonna kind of go in a different direction. So I wanted to pause here for any questions that people might have about this. All right, great. Of course, all I've done is sort of like give a bunch of results without really discussing mathematics. So it's hard to have questions. So let me maybe say a little bit more. And now, so the next thing I want to introduce is contact geometry. And the reason for this is contact geometry is, in some sense, the source of a lot of these type of phenomena, this type of flexibility construction type phenomena. The downside is contact geometry is, it's a little bit difficult to introduce maybe, or it's a little bit unintuitive why it's kind of a good definition. So the way I'm gonna kind of principally talk about it here is if I have any manifold Y, and so Y is an odd dimensional manifold, then of course I can just take R times Y and then just talk about the kind of shifting action. And so now I can talk about a symplectic structure on that, which is equivariant with respect to that action, right? Like, and instead of being like literally invariant, I want it to be kind of exponentially expanding with respect to this. Now, the reason for this is it gives a kind of good notion of convexity. And this has kind of its roots really inspired in high dimensional complex analysis, which basically comes from the fact that, like, if you take Cn minus the origin for n bigger than 1, then the outside of kind of Cn looks different than the inside of Cn. There you have this kind of Hartog type phenomenon. There's a notion of convexity in complex analysis, I guess is the point. And similarly, there's a notion of convexity in symplectic geometry, which is what's kind of captured by this exponential expanding. And so by definition, a contact structure is just this sort of the kind of equivariant structure near a kind of infinite collar of a convex boundary. And so this is kind of just saying, again, what I have said, but the point of this definition is that if you have an affine variety, just like in Cn, so you have some sort of complex manifold, and that in particular is a symplectic manifold, then you would like to make sense of kind of its boundary at infinity. Like, what is that geometry? Is there a way to just kind of talk about that? And contact geometry is the way to do that. In fact, not only is this kind of boundary at infinity a well-defined contact manifold, but also, if we're talking about symplectically, this is almost kind of an if and only if type of statement. So yeah, so the way to think about contact structures, I think, is kind of as the boundaries of symplectic structures, particular kind of like infinite boundaries. Now, this is not the usual definition. Typically, it's defined intrinsically. If you define it intrinsically, it's a hyperplane field, which is non-integrable in a certain way. It's also typically defined by a contact form. I'm going to kind of brush this under the rug a little bit. Here's just kind of a picture of one. So as I mentioned, a contact structure is given as a a hyperplane field. Here's a picture of one. And in fact, every contact manifold can be built by just gluing this ball together with itself via maps preserving this hyperplane field. So one way to think of it is just an atlas covering a manifold via diffeomorphisms preserving this specific plane field. And that's an elementary theorem. That's called Darboux theorem in the field. Okay, yeah. So now one question is just what three manifolds admit a contact structure? And turns out this is somewhat classical result, which is that every three manifold does. Now, in fact, there's a slight refinement of this. And so, in fact, it's not only that like each manifold admits a contact structure. This is a result from far in the future. No, I'm joking. It's, of course, 1971, not 2971. Given any diffeomorphism type of the manifold, and also given any topological type of the two-plane field, forgetting the non-integrability condition, but just thinking about the two-plane field, you can in fact realize anything by a contact structure. Now, anyways, something I want to highlight about this is that to prove this theorem, it suffices to prove it locally, right? Because if you could prove this theorem locally relative to arbitrary boundary conditions, then you can prove the theorem globally because you just take a covering and then you just like induct, right? Like, I mean, there's, yeah. So something that I'm wanting also to highlight for this is that a lot of the way that these kind of general results are proved, whereas kind of like, oh, you have any topology and you can do this, or you have any topology and you can do that. Really, the way you prove that is you don't use the topology at all. You just prove a sufficiently robust local theorem, which I guess is not so surprising in general, but what's so surprising maybe is that it is possible to do this despite the fact that there are what we know to be very very tightly controlled, rigid geometric constraints on the situation. Okay, so now in higher dimensions, it's not true that every manifold has a contact structure, because remember, this is what is a contact structure. It's kind of like what does affine variety look like at infinity, right? So in particular, it has a stabilized complex structure just on its tangent bundle. So not every smooth manifold has one. But of course, that's a topological obstruction. I'm not talking about any sort of holomorphic structure here. I'm just talking about topological obstruction, and you can measure this. This is some algebraic topology language if you're not in the field. But yeah, so these are kind of the right terms to phrase things, right? And so now it was proved starting about 10 years ago that also this Lutz-Martinet theorem generalizes to, well, first 5 dimensions, that any stable, almost complex structure can be realized geometrically by a contact structure. And that's in fact true in all dimensions, which is proved by Borman and Eli Ashberg and myself. Yeah, so great. Anyways, so this is kind of a useful thing. Now, let me think. So I'm about halfway and 12 slides. Okay, that's about perfect. Yeah, maybe I'll just pause here because I know I've gotten into the contact geometry and that can a lot of times be a stumbling block. I think the way to think about this is kind of regardless of what that geometry is, it is this sort of particular odd dimensional geometry, which is kind of tightly related to complex and symplectic geometry. But, yeah, that's, yeah. In any case, if there are any questions. All right, great. So now something I want to talk about now is kind of uniqueness. So this is kind of an existence result, right? Like it's just kind of given any topological type. Notice all the input here is a smooth manifold and a complex structure that's like up to homotopy. So, that's all kind of topological input, but it's giving geometric output, which is a contact structure. Now that's an existence result. What can we say about uniqueness? Now something that's kind of nice about the topology of contact structures, or the geometry of contact structures, is that inherently they do not have moduli. So a deformation is an isotopy, and what that means is that uniqueness is the same thing as parametric existence. To spell that out a little bit, so if you have two contact structures, and first of all, if they're homotopic among complex structures, they better be, then as long as we can kind of run this existence proof in a way that is, smooth in families, then for every kind of, if I have a homotopy between the complex structures, then for every T in that homotopy, I just realize it by a contact structure. And then we get this family of contact structures, psi T, interpolating between them. And then they're contactomorphic because any homotopy is, realized by an isotopy by what's called Gray's theorem, which is a very classical theorem. So yeah, now that doesn't work, and that there's kind of no hope ever that that could work because it's just a fact that was known kind of long before any of this flexibility stuff, that that uniqueness is just false. There are many distinct contact structures which are kind of topologically the same. So you cannot prove a uniqueness theorem because it's false. However, even though I kind of just made a compelling argument for why, if you know existence, probably uniqueness should also follow. So that doesn't work, but it kind of like maybe works like a little bit given some extra hypothesis. The point is that making it smooth in families is hard because you do a lot of cut and paste sort of stuff. But if you think a little bit harder and use an extra hypothesis, you can make that work. And so that's also kind of part of this theorem that we proved, is that not only does any stable almost complex structure have a contact structure, but there's a unique over twisted contact structure. And this is, again, is this sort of flexibility type results. So this is something I wanted to discuss. This is also building on earlier work of Ellie Ashberg from, I guess, 25 or no, 35 years ago now. Well, not 35, 32, but yes, where this is kind of a phenomenon that is kind of understood for three manifolds. Okay, great. Now, something I want to point out about this definition, or this theorem, is that this is not an interesting theorem, right? Because like if you want to say that like, oh, well, you don't have uniqueness, but among this class you have uniqueness, like, well, that only means something if you understand that class, right? Like, so the important part about over twistedness is it's similar to these other phenomena which we've seen, which is basically that what I'm calling here is the semi-locality, which just means that it's defined by containing something. So if you have just like a little bit of this thing, then you just are over twisted, and then you become inside of this flexible class where anything is possible. Everything's ruled by kind of topology. And so because it's defined by containment, if you're just over twisted in one place, that means you're over twisted. You don't have to be over twisted kind of everywhere. You just have to have a little bit of over twistedness. And that's really the kind of essential point of this class. So to give I think a nice example of this, let's just talk about what are the contact structures on S5. So I have S5, so that's a manifold. It has some contact structures. And the thing that I like about S5 is a couple things. So first of all, there's a unique, stable, almost complex structure. And so that means that all this extra topological data that we need to keep track of, actually, we don't need to keep track of it because it's trivial in this case. But also maybe more important, there's a notion of connect sum, where if you have a contact sphere and you have a contact sphere, you can stick them together and you get a new contact sphere. So that gives a monoid structure that's a commutative associative operation. And we don't know very much about this monoid, but let me tell you what I do know. So first of all, it has an identity element, which is the boundary at infinity of C3. So that's a kind of nice thing. So it's countable. That's elementary is maybe a bit, but it's it comes from the fact that there's like no moduli and there's finitely many charts and dot. It's one of those type arguments. But it's not finitely generated, and that kind of follows from these kind of Ustalovsky type results. This is, I think, really kind of explained very nicely with something called like asymptotic Euler characteristic by Quan and Van Coort. So that's a huge like module. In particular, they show that it's not finitely generated by constructing a submodule which surjects onto Q. So that's a pretty big module. So what overtwistedness is saying is that there is a zero element to this. There is the overtwisted contact structure, and that is a geometry which kills every other geometry. So if you have the overtwisted sphere, and then you have one of these other spheres, which come from this huge and extremely diverse class of contact structures on the sphere, but if you stick it on the overtwisted one, all that's lost. It's just overtwisted now. So this is a geometry which kind of destroys other geometries just by being in its presence. And it's, I think what it really kind of demonstrates is that though we have this sort of wide diversity of contact structures, they're sort of delicate in that they require, you need to understand their kind of entire global structure in order to understand how they're different, I suppose. Just to point something out, in general, it's poorly understood. We don't know if there's any units, meaning things that are non-standard but sum to the standard thing. We don't know if there are zero divisors, meaning non-overtwisted things, which sum to the overtwisted thing. There's not even a conjectural isomorphism type of this monoid. This is just, you'd think it's like, it's S5, like how bad could it be? This is just so far beyond us. Okay, great. So now, what's the connection between these sort of things? I talked a lot about Lagrangians in the beginning, and then I kind of like took a hard turn and I introduced this contact geometry, and I'm talking about this a lot. Now, you can kind of see maybe there's an analogy, but it turns out these things are not directly connected, but they both have the same flavor of if you give me an inch, I'll take a mile. Now, of course, nobody uses these old-fashioned units besides us in the United States, but it's maybe a bit more poetic. But the point being that, like, if you have just a little bit of this geometry, which is sort of destructive, then kind of anything becomes possible. And you kind of see this within this overtwisted contact structures. You're also seeing this within Lagrangians, these XPs. That's that sort of phenomenon I'm wanting to really highlight. Yeah, and this is, I think, just kind of saying what I've said. So this appears in a lot of places, particularly even its contact geometry, I would say, even more than symplectic geometry. Of course, they're closely related. Both is kind of like the boundary of the other, but it's really the contact geometry that I think is more the source of this, it seems. So the results above, these ones about construction of these Lagrangians and the ones about these manifolds XB, come from a different area both in contact geometry, but different from over-twistedness, and this is due to something called loose Legendrians. Yeah, now this I'm maybe going to go over a little bit fast because I'm going a little bit behind on time. So what a Legendrian submanifold is it's the same thing as a Lagrangian, except now we're in contact geometry. So one way to phrase it is it's something which is tangent to this kind of hyperplane field, which is hard to be tangent to. Maybe better to think of it as just like, okay, so a contact structure is just an equivariant symplectic structure. So a Legendrian is just an equivariant Lagrangian. And so these, of course, I'm among a community of people who study Legendrians just to study them, but particularly connecting to symplectic geometry, there's two major kind of connections. One of them is that if you have just an isotopy of Legendrians, well, you can kind of suspend that to build a Lagrangian in this kind of R cross Y. It's no longer equivariant, but it's still a Lagrangian, and so you could use that for constructions. The second major connection is that you can use it sort of as construction, as sort of directions or blueprints to construct manifolds out of, kind of gluing instructions. And that's how we kind of understand symplectomorphism types of manifolds. So now, like anything, this is a geometric notion, but we can kind of put on our algebraic topology glasses and you get a weaker notion. This is something we call a formal Legendrian. The specifics of it, I won't worry about too much. There's an existence result for these going back to 1990, which is that any formal Legendrian is smoothly isotopic to a genuine Legendrian. Something I want to highlight is that this is, because this is gluing instructions for manifolds, this shows that any smooth manifold which has half-dimensional homotopy type, and of course you need a complex tangent bundle, then you have a symplectic structure on this manifold. In fact, you have a Kähler structure on this manifold. So here, I want to note that the hypothesis that we're in high dimensions is essential. It's false. In R3, there are formal Legendrians which cannot be realized geometrically. And that's related to the fact that there's no symplectic structure on S2 cross R2. That's kind of a very specifically four-dimensional phenomenon. Nothing like that happens at high dimensions. Okay, yeah, so loose Legendrians, now this is kind of similar maybe to over-twistedness. We have existence of Legendrians, at least in high dimensions, right? Any formal Legendrian realized by a class. That's, again, of any smooth type and inside of any contact manifold. Uniqueness, again, fails. We wouldn't expect it to be true. It's been kind of false for a long time now. But it is unique in some kind of specific subclass, and that subclass is still kind of semi-local. And so that if you're loose kind of in just one portion, then you're loose everywhere. And then once you're loose everywhere, then you kind of don't have geometry and you're kind of amenable to topological sort of understanding, I guess. Now, why is that useful? So let's go back to this XB theorem. So I mentioned that all of the XBs for higher B, those are all the same as each other, right? That's kind of a surprising theorem, considering X1 is different, right? So the way to think about this is that all of them, including B equals 1, is that you have a 6 ball and you have another 6 ball and you're gluing them together along some Legendrian S2 in the boundary 5 ball. That's true, doesn't matter what B is. that's not so obvious, but it's true. So for B equal 1, it's just a different Legendrian, which isn't loose. It's in this rigid class. In fact, it's the standard unknot. But for B equals 2, it's already kind of the loose Legendrian. And for B equals 3, it's kind of like more loose. And for B equals 4, it's even like more loose. So you kind of have like extra loose things. But the whole point of this kind of flexible class is that there's no such thing as being like more flexible. Once you're flexible, then you're just kind of completely topologically classified. And so everything becomes the same. So yeah, so this is really the source of this sort of thing. It has to do with the kind of the similar kind of dichotomy results, but for the gluing instructions of these manifolds. This is another example. I like it a lot because it's a complicated picture. This is also due to Casals and myself. Same as this XB result. So this is a Corus-Russell cubic, is some hypersurface in C4. It's famous, it was studied by Corus and Russell because it's diffeomorphic to R6, but it's not algebraically isomorphic to C3. So we were able to show that, in fact, it's symplectomorphic to C3. And we did this, well, obviously you can't understand this without me doing a lecture on what these diagrams mean, but this is kind of a picture of the Corus-Russell cubic. And you can kind of do some sort of simplifications. This is some sort of like Kirby calculus type of language. But this thing that's highlighted in green, this sort of zigzag figure, is this sort of manifestation of this flexibility. And once you see that anywhere, then everything falls apart. And it's just C3 because C3 is the kind of minimal topological model. Anyway, just kind of a fun thing. So the other thing that I talked a lot about kind of at the very beginning was constructions of Lagrangians, right? This fact that like if you have any 3 manifold connects them as 2 cross S1 or, these sorts of things. So why is this related? So now I mentioned with this loose Legendrians that like it shows that if you have 2 different Legendrians, then it's unique up to isotopy as long as they're loose, right? That is to say that it constructs an isotopy, right? So what this loose Legendrian classification theorem is doing when it says that things are unique, what it's really doing is it's a machine for constructing isotopies in the presence of this looseness, whatever it is. Like, and so, well, whatever it is, if it's a machine for constructing isotopies, well, you can suspend those, just, take the graph of them for every t, and that gives you a Lagrangian with specific boundary conditions. And of course, that's useful. So these constructions that I mentioned earlier, those kind of come from that, I guess. Now, of course, these constructions work for very general L, and they come from the suspensions, but now the price for that, what you need is, you can only construct isotopies for loose Legendrians, right? Like, so you need a source of that kind of flexibility. That's always kind of going to be this funny geometric model. You can take it to be S2 cross S1. In fact, you can take it to be S2 cross Sn minus 1 in general dimensions. A negative self-intersection point also works. Figuring out what geometries work and how they work is, interesting questions, but you need somewhere to start from. Again, this is not specific to even dimensions. This is not specific to 3 manifolds. It's not specific to Cn. This works inside of arbitrary symplectic manifolds. Any dimension, we do need this high dimensional. 4 dimensions is way different. But besides that, anything works. Despite this working in kind of very general situations, though, this flexible model that you kind of need to get started, in general, it's for symplectic experts, this is kind of non-monotone, and so it makes it sort of very difficult to analyze any of this from floor theoretic perspectives. there definitely are things that can be said, but it's quite subtle, I guess. It's not. You get curvature terms, I guess, in the A infinity structure. Anyways, yeah, so something else I just wanted to kind of highlight for the end is just a lot of the recent progress. Yeah, I guess I've been speaking a lot about my own work mostly. I suppose, that's, well, one, I'm an expert in it, and I guess if you're being awarded for something, then you feel, but really, I think, really, I'd love to highlight a lot of work of colleagues and of mine, because especially a lot of the recent stuff is they just have exploded. For instance, if we're talking about contact structures and you're looking at codimension 2 hypersurfaces here, this has completely changed in the last couple years. That's both in the isocontact case and in the case of the free domain, which is actually much more powerful, I would say. And that also has to do with an H principle for convex hypersurfaces. That's real codimension 1, extending Giroux flexibility. I didn't talk much about this, but this is also kind of a landmark flexibility theorem from maybe about 20 years ago now. Yeah. Something else that's seen a lot of rapid progress is angle geometry. This is particularly interesting because you see these same sort of rigid and flexible sort of dichotomies, where some things are rigid and some things are flexible, these sort of over twistedness or looseness type dichotomies. Just a couple of these, kind of the largest sort of dichotomies was Casals, Delpina and Presas, and Delpina and Vogel a few years ago. There's been a number of other things, specifically in angle geometry, about Lagrangian embeddings, tangent embeddings, transit, all kinds of things, most of them by some subset of these 4 authors. Also, regular Lagrangians and Weinstein manifolds and Weinstein structures have seen a lot of recent progress. Eliashberg, Ganatra, Lazarev, and in particular, Lazarev has done a lot of cool things with Weinstein structures, particularly using this to get some interplay with things like Rapp-Fukaya categories, and yeah, being able to really get sort of kind of rigid miles out of flexible results, which is really cool. There's some more things, some existence results for Liouville cobordisms. This is kind of using more the over twistedness theory. This gets into conformal symplectic geometry, which has seen a lot of cool work. We actually just had a conference about this. Some other things is simplification of front singularities. So some cool work that Danny Alvarez Gavella was doing. It's also this arborealization project that is also kind of closely related to H principle type arguments. This kind of goes on, but what I'm really wanting to highlight, not only to highlight a lot of really cool work that's been going on, but something I wanted to kind of point out is that I'm highlighting a lot of this recent work, not only because it's the recent stuff and it's really cool and cutting edge, but this is kind of all new. More than 10 years ago, this was a field that kind of didn't really exist all that much. So it's really cool to see all the exciting different just kind of directions that people are taking with these sort of perspectives, I guess. Yeah, so it's great to see the future. Great, so that's everything. Thank you very much. And yeah, please let me know any questions.
I think we should all thank Emmy for the great lecture. So many deep results, really very nice. And probably congratulate her again for the MCA prize. And yeah, I think it's a good time for questions. So let's see if anyone has raised hands, but
Huh.
let me see the chat.
So I see one from Alejandro about the question about what's the problem with n equals 2. So there's a lot of different perspectives on this. One of the most high level you could say is that like interactions with Seiberg-Witten theory and things like genus functions just really produce a lot of unique obstructions. On the flexibility side, I can give kind of a more cute answer, which is that the Euler characteristic of any submanifold of R1 is positive. And it turns out that that's a big problem for us. But I mean, more seriously, the fact that you have negative Euler characteristic things in Rn is an important thing for kind of causing things to unfold in higher dimensions. But that has to do, of course, with the fact that Euler characteristics of surfaces are negative and things like that.